Hello, this is Professor Kuehn. In my last lecture, I gave a short history of the debate between geocentrists and heliocentrists, and then I talked about Kepler's 3 laws of planetary motion. And now what I'm going to do is I'm going to make my way into Newton's Principia, Book 3. He titles this section the Phaenomena, which is basically saying I am going to talk about the things that we observe in nature, specifically regarding our solar system, or the system of the world, as he would say. So there are 6 separate phenomena that he wants to talk about. And after we go through these, then we will finally be in a position to articulate his universal law of gravitation. So let's begin with phenomenon 1. This I have printed on the screen here. So I'm just going to read it and then I will explain what it is that he's talking about. Okay, so phenomenon 1 says that the circumjovial planets, by radii drawn to Jupiter's center, describe areas proportional to the times of description, and that their periodic times, the fixed stars being at rest, are in the sesquiplicate proportion of their distances from its center. So what is Newton talking about in this section? Well, we have to understand some of his terminology. So what does he first of all mean by the circumjovial planets? That's the subject of this sentence. He says the circumjovial planets, well, circum means around, and Jove is another name for Jupiter. So the circumjovial planets are the little planets that are going around Jupiter. We now know them as Jupiter's moons. At the time that Newton is writing this, they had just been discovered by Galileo. Galileo, turning his telescope to Jupiter, had discovered in a book that he wrote called The Starry Messenger, in about 16 or so, discovered these 4 of Jupiter's moons. He called them the Medicean stars because he named them after his funding agency, the Medici banking family. He called them the Medicean stars. Here, Newton is calling them the circumjovial planets. In any case, the idea is that if you look through a telescope at Jupiter, so if you can find Jupiter in the sky, so this is Jupiter, you will notice that there are 4 little bright dots that lie in a line compared to Jupiter. And Galileo identified these as 4 planets. Of course, now we know that there are many more planets or moons of Jupiter, but these are the 4 biggest ones. And so what you can do is by looking at these, you can look at the distance they are from Jupiter, and they kind of move around compared to each other from night to night. And this is precisely what Galileo was able to see. So this is kind of a side view of the moons of Jupiter. If you look at it from the top, which we don't, you would see that these moons are actually going around Jupiter. That's why they're called the circumjovial planets. These 4 moons are all going around Jupiter. But when we look at it, for instance, from the side, like over here from the Earth, this is our eye looking at it, we would just see them kind of in a line with Jupiter, going at different distances from Jupiter. And that's what we're seeing over here. Okay, so that's the idea. We're talking about the circumjovial planets. He says by radii drawn to Jupiter's center. So if you were to draw a diameter or a radius from the center of Jupiter out to the location of a particular planet, that's the radius drawn from Jupiter's center, these describe areas proportional to the times of description, and that they're periodic. Okay, so what does that mean? So if you were to look at one of these planets going around, one of these moons going around Jupiter, you would notice that in equal times, they sweep out equal areas. Okay, so the area that this sweeps out, this is a terrible drawing right here, but the area that this sweeps out in a given time, looking from above, which you could deduce from looking at it from the side, they have equal areas in equal times, or the area is proportional to the time of description. Okay, so that's the first point he makes. Areas are proportional to the times of description. And secondly, that the periodic times, and this is an aside, the fixed stars being at rest, are in the sesquiplicate proportion of their distances from the center. So for example, if you were to pick out any 2 of Jupiter's moons, let's say Jupiter's moon number 1 and Jupiter's moon number 2, and you were to measure the time they take to get around Jupiter, you were very patient, you were watching these night after night after night, you notice this moon starts out here, over time it goes over to here and then comes back to here, that would be the time of orbit of that planet, and this one you might see goes to here and back to here, that would be the time of orbit of that planet or that moon. You would notice that they go in the ratio as the distances from Jupiter to the 3/2 power. Okay, so they're in the sesquiplicate proportion of their distances from its center. Okay, that's the point that he's making here. Now you might be able, if you've been paying attention to Newton's proposition 4, corollary 6, and so on, this is going to imply that there's a force pulling these moons toward Jupiter, and then that force is a 1/r² force. He doesn't mention that here, but that's something he is going to get at. Okay, let's look at the data table. So I'm going to add an image here, and we'll look at a particular data table. This is table 26.1. This is the data table that he presents as evidence of this. Okay, so table 26.1, this is a comparison. This is, by the way, from chapter 26 of a student's guide through the great physics texts. This is data that had been collected up to this point. A comparison of the observed orbital sizes of Jupiter's moon to the calculated sizes based on Kepler's third law. So this right here is the periodic time of Jupiter's first satellite, its first moon. This is of the second satellite or second moon. So this would be moon number 1, this would be moon number 2, this would be moon number 3, and this would be moon number 4. So for example, moon 1 takes 1 day, 18 hours, 27 minutes, and 34 seconds to go all the way around Jupiter. Moon 2 takes 3 days, 13 hours, 13 minutes, and 42 seconds, and so on. Up to the fourth moon takes 16 days, 16 hours, 32 minutes, and 9 seconds to go around Jupiter. Okay? Now, that's the periodic times, so that is where we're considering, we could compare any two of these times, for example, time 1 to time 2. And this latter half of the table, what Newton is doing is presenting the most recent data on the distances of these satellites from Jupiter's center. So for example, these are all measured in semi-diameter of Jupiter, or radius of Jupiter. So for example, Borelli, this was a scientist, measured that moon number 1 gets up to 5 2/3 Jupiter radii from the center of Jupiter. So if that was, for example, this moon right here, the distance or the radius it would get from Jupiter would be almost between 5 and 6 times the radius of Jupiter. So if you look at this distance right here, maybe that's some very tiny distance. This is 5 or 6 times as far as that. Okay? Satellite 2 gets about 8 or 9 times Jupiter's radius from the center of Jupiter. Moon 3 gets 14 Jupiter's radii away from Jupiter. And moon 4 gets about 24 or 25 Jupiter radii away from Jupiter. There's another scientist named Townley who measured, he got this result. Cassini, there's a Cassini satellite, by the way, that has been out exploring the solar system. Anyway, it's named after the scientist Cassini. He measured it to be 5, and he measured it again to be 5 2/3. So what Newton does is he recognizes these are all about between 5.5, 5, 5.5, 5 2/3, okay? And then you could look at satellite number 2, and you could compare these. You could form the ratio of this to this, and take it to the 3/2 power, and you would get about this right here. And you could compare to, so that would be the average of the distances, that would be the average of the times that you get from the periodic times, and you could find that this is basically in agreement with these numbers. In other words, that Kepler's third law seems to hold. So this is the upshot, is that Kepler's third law seems to hold, or seems to be true, for Jupiter's moons. That is, they orbit Jupiter, and when you compare the orbital times and the orbital radii, they follow Kepler's third law. And again, this is going to be important in establishing Newton's law of gravity. Okay, let's look quickly at phenomenon number 2. Phenomenon number 2 is very similar. So I'm going to open this, add image, go down to phenomenon 2. Okay, so here we are. So phenomenon 2 says that the circumsaturnal planets, by radii drawn to Saturn's center, describe areas proportional to the times of description, and that their periodic times, again, the fixed stars being at rest, are in the sesquiplicate proportion of their distances from its center. Okay, so once again, if you were to look through a telescope at Saturn, okay, so here's Saturn, you would notice that it has some moons. I don't recall offhand how many moons it has, and you can measure the time it takes a particular moon to go around Saturn and come back to its same spot. You can measure the distance that it is from Saturn, and you could compare the distances of these moons from Saturn. And let's import the data that Newton provides us with. Here it is. Okay, so here we've got, I guess, 1, 2, 3, 4, 5 moons of Saturn that were known at this point. Moon 1, Moon 2, Moon 3, Moon 4, and Moon 5. And here are 5 moons right there. These are the times of orbit around Saturn. The shortest one takes about 1 day and 21 hours, almost 2 days. The farthest away one takes 79 days and 7 hours to go around Saturn. And then one could look at the distance that each satellite or each moon gets from Saturn's center, again, measured in semi-diameters or radii of its ring, apparently. That's a standard that's being used. The Saturn's rings were recently discovered by Christian Huygens in the 1600s. He's someone we studied in Physics 202. Anyhow, you can look at the distance. For instance, satellite 5 gets 24 Saturn radii away from Saturn. And you could look at whether or not the distances between Saturn and the planet and their periodic times follow this ratio given by Kepler's third law. And once again, he finds that, first of all, I guess I skipped over something. First of all, the areas that are swept out by these moons are proportional to the time you're considering. And secondly, that the periodic times are in the sesquiplicate ratio of their distances. Okay, so again, this is that if the areas are proportional to time, that implies, so area proportional to time. According to Newton, he's going to say this implies that there must be a centripetal force, and that the Kepler's third law holds. These are the radii or the semi-major axes. This is going to imply that the force goes as 1 over r squared. Whatever force there is holding these in orbits must be a 1 over r squared force. Okay. Again, Newton hasn't said this specifically yet. He's just helping us to understand what we see regarding Jupiter's moons and Saturn's moons, but this is eventually where he's going with this. Okay, and I think what I'll do is I will stop there and pick this up with phenomenon 3 through 6 next time.